Thank you for tuning into the poster presentation of the paper Augmenting Genetic Algorithms with Deep Neural Nets for Exploring the Chemical Space. This is work done jointly by me, Pascal Friedrich, Mario Kren, and Alanis Burguzik. Let me first begin by explaining the genetic algorithm of our approach. We start off with a set of molecules M. Of course, this can be derived from any source. And we evaluate each of those members with an external property evaluator. In this case, we make use of the commonly used penalized log p metric defined in literature. We incorporate these property evaluations, J of M, into our fitness function. The fitness function essentially steers the genetic algorithm. In a typical evolution style approach, we keep the most fit or best performing molecules and get rid of the bad ones. In our case, we replace the bad molecules with random mutations of the best ones. We keep repeating this process for multiple iterations, where each iteration is a generation. For the mutations, we make use of the SELFIES representation. Why SELFIES? Well, SELFIES are 100% valid. So we can essentially make any mutation to a SELFIE molecular string representation, and it will be syntactically valid. This is contrary to the SMILES representation, where mutations don't necessarily lead to valid molecules. On top of the genetic algorithm, we have a neural network discriminator. This can be viewed in a typical GAN-like fashion, where you have fake data being proposed by the genetic algorithm and real-world samples coming from the data set. In this case, a subset of the Zinc database. We incorporate the predictions of the neural network discriminator into our fitness function. Notice that we have a parameter beta on the discriminator predictions D of M. Now, we observed that by tuning beta, we can essentially mimic the properties of our dataset. Have a look at beta equals to 50. Here, the average J of M produced by the genetic algorithm is close to 0. This matches the properties of the reference dataset. And if we set beta to really small values, where we are incorporating less of the discriminator predictions, we are essentially only giving the genetic algorithm the objective of maximizing the penalized log p score. On the right is just another way of representing the same information. Now, we observe that if we run our genetic algorithm for long periods of time, it essentially proposes same molecular families for multiple generations. We call this convergence, and we approach this problem as a local minima trap. By incorporating a time adaptive penalty of the discriminator, I urge you to look at the paper for this, look at the paper for a deeper explanation. We can essentially avoid this problem. Notice that one color emerges and eventually dies off, getting replaced by another one. This basically indicates new molecular families being generated, being killed off, and repeating itself, essentially creating a self-perpetuating algorithm. Now, we can view our performance on the penalized log p objective. The goal was to just maximize this objective. Here, with the genetic algorithm, we have 12.6. The genetic algorithm with the discriminator for a fixed beta, we have 13.3. And this is the time-adaptive genetic algorithm with a d of t indicates a time component with 20.72. Essentially, there's no saturation here, and so the algorithm keeps exploring. In this experiment, we start off with a known set of 800 molecules. Our objective is to maximize the penalized log p score while preserving a similarity to the starting structure. We can see that we have a large improvement while having a high success rate. Here's an example where we start off with this structure and we optimize it to produce this one. Same here. You can notice that the final structure is somewhat similar to the beginning one, and this is what the deltas refer to, the similarity constraint. In this one, we have a delta of zero point 0.6 and zero point 0.4. Thank you for your time, and if you would like to have a look at the code and the paper, it can be followed at this links. Thank you.